How does login with Google actually work? You click one button, you never type a password into that random app, and a second later you are in. No new account. No, please create a username. It feels like magic, but it is not. Underneath that button is one of the most important patterns in all of software. The thing that lets a note-taking app read your calendar, lets your bank talk to an accounting tool, and lets millions of apps log you in without ever seeing your password. In the next 10 minutes, we are going to pull that button apart completely. Two ideas do all the work here. One is about permission and the other is about a small, self-contained ticket of trust. Get these two and half the modern web stops being mysterious. Think about what you're really doing when an app wants your data. Say a photo printing service wants the pictures in your Google account. The lazy, dangerous way to solve this is obvious. The app asks for your Google email and password, logs in as you, and grabs the photos. Please never do this. If you hand over your password, that app can now read your email, empty your drive, change your settings, everything. You gave it the keys to your entire digital life just to print some photos. And if that app later gets hacked, your password leaks right along with it. We needed a way to say, yes, you can see my photos without saying here is my password and full control of my account. That exact problem is what this whole system was invented to solve. Here is the one idea that unlocks all of this: delegated authorization. That is a fancy phrase for a simple move. You let one app do a specific thing on your behalf without ever giving it your identity. On screen you will see the real name for this: open authorization, usually written OAuth. The key word is authorization. What are you allowed to do as opposed to authentication, which is just proving who you are. With this pattern, you never give the app your password. Instead, you tell the provider, Google, in our example, I approve this app for this one job. The provider is the one holding your password, and the provider is the one that hands the app a limited pass. You stay in control the whole time, and you can take that pass away later. That single shift is the entire game. Picture a valet key for a moment. A lot of cars used to ship with two different keys. Your main key opens everything: the doors, the trunk, and the glove box where you keep your documents. But the valet key is deliberately weaker. It starts the engine and unlocks the door, and that is all it does. It will not open the trunk, and it will not open the glove box. You hand it to a stranger at a restaurant precisely because it can only do a little. That is exactly what this login system gives an app. A valet key to your account, not your house key. The app can do the one thing you allowed: read your photos or see your email address, and nothing beyond that. If someone steals that valet key, they still cannot open the trunk. Hold on to this image, because everything that follows is just the mechanics of cutting a valet key for the web. So here is the actual flow, step by step. This is the famous redirect dance. Three parties are on the floor: you in your browser, the app that wants access, and the provider that guards your account. Step 1, you click Login with Google, and the app sends your browser over to Google. Notice you are now on Google's real site, not the app's. Step 2, Google checks who you are and shows you exactly what the app is asking for. Step 3, you approve, and Google sends your browser back to the app carrying a short, one-time code. Step 4, in this part happens quietly in the background. The app takes that code and trades it with Google directly for a token. Why the extra trade? Because the code travels through your browser where things can be seen, but the final token is swapped server to server out of sight. That handoff is the heart of the whole system. That permission screen you have seen 100 times matters far more than it looks. When Google asks this app wants to view your photos, allow, it is showing you the exact shape of the valet key before it gets cut. Scopes are the specific permissions: view your email address, read your calendar, upload to your drive. A well-built app asks for the narrowest scope it actually needs and nothing more. That is why a login button that only wants to confirm your name and email should never be asking to read your private messages. You are the one who approves, so this screen is your moment to actually read what you are granting. Grant the trunk and the glove box too, and you have handed over a house key after all. What the app gets back is not your password, it is an access token. Think of it as a stamped, temporary pass. It says the bearer of this pass may view this person's photos until this time. The app attaches that pass to every request it makes to Google, and Google checks it. And here is the part worth remembering: that pass is deliberately short-lived. In a lot of systems, the access token is good for only about an hour, 60 minutes, and then it simply stops working. 60 minutes and it is dead. After that, the app has to quietly fetch a fresh one behind the scenes using a separate, longer-lived refresh token. Short lifetimes are a feature, not a bug. If a token ever leaks, it becomes useless almost immediately. A stolen valet key that self-destructs within the hour is a pretty safe valet key. Now let us talk about what that token actually is, because it is not random gibberish. Very often that pass takes one specific self-describing format. On screen you will see its name: a JSON web token, though most people just call it a signed token. Here is the clever bit. A boring token is just a random string. The server has to look it up in a database every single time to find out who it belongs to. A signed token flips that around. It carries the information inside itself in a way the server can trust without looking anything up. The token literally contains "this is user 42, they can read photos, this expires at 4 o'clock. All packed inside and stamped so it cannot be faked. Self-contained and verifiable, that combination is why this format quietly runs a huge slice of the modern web. Every one of these tokens has exactly 3 parts, and once you see them, you can never unsee them. It is 3 chunks of text separated by 2 dots, header, then payload, then signature. 3 parts every time. On screen, watch them light up in 3 different colors. The first part, the header, is small. It just says what kind of token this is and how it was signed. The second part, the payload, is the actual content, who you are and what you are allowed to do. The third part, the signature, is the wax seal that proves the first 2 parts have not been touched. Each part is just text that has been encoded into a compact, web-safe form, not encrypted, only encoded, so it survives being passed around inside web addresses and headers. Header, payload, signature. Learn those 3 words and you understand the whole token. The middle part is where the interesting stuff lives. This is the payload, and it is a small bag of facts called claims. A claim is exactly what it sounds like, a statement the token is making about you. There is usually a subject claim that says which user this is. There is an expires claim, a timestamp marking when the pass goes dead. There might be claims about your role, your email, or which app this token was minted for. When a server receives the token, it reads these claims directly and instantly knows. This is user 42, they are an admin, and this pass is still valid for 20 more minutes. No database round trip, no session lookup. The answer is sitting right there in the token. That is what self-contained really means in practice. So what stops someone from just editing the middle part? Because if the payload is only encoded, not encrypted, anyone can decode it, change user 42 into user 1, the admin, and re-encode it. That is where the third part earns its keep. When the provider creates the token, it takes the header and payload, mixes in a secret key that only the provider knows, and runs them through a one-way function to produce the signature. When a server later receives the token, it repeats that exact calculation with the same secret and checks that the 2 signatures match. Change even a single character of the payload and the recomputed signature no longer lines up. The token is rejected on the spot. You cannot forge the signature without the secret, and the secret never leaves the server. So the payload is readable by everyone, yet editable by no one. That is the whole trick. Here is why developers love this so much. Traditional logins keep a session in the server's memory or database. On every request, the server looks you up to remember who you are. That works, but it means every server has to reach the same store, which gets painful once you have 20 machines sitting behind a load balancer. A signed token deletes that problem. Because the token proves itself, any server that knows the secret can verify it on the spot. No shared session store, no lookup, no chatter between machines. That is what stateless means. The request carries its own proof of who you are. It is why signed tokens are everywhere in microservices and mobile apps, where dozens of separate services all need to trust the same login without phoning a central database on every single click. Now for the trap that burns almost everyone, and it might be the single most important sentence in this whole video. Signed does not mean secret. The signature proves the token has not been changed. It does absolutely nothing to hide what is inside. Anyone who gets hold of the token can paste it into a free online decoder and read every claim in plain text. Your user ID, your email, your role, all of it. So never, ever put anything sensitive in the payload. No passwords, no card numbers, no private secrets. A signed token is like a postcard with a tamper-proof seal. You can trust that nobody rewrote the message, but the mail carrier can absolutely read it. Treat everything in the payload as public information, because to anyone holding the token, it effectively is. Let us ground all of this in real products you already use. Use case 1, the login button itself. Log in with Google, sign in with GitHub, continue with Apple. Every one of those is this exact redirect dance, handing the app a token instead of a password. That is why you can sign into 100 different apps and only ever really trust Google or GitHub with your actual credentials. Use case 2, services talking to each other. When your company's billing service calls its shipping service, it does not send a username and password. It sends a signed token that proves I am the billing service and I am allowed to do this. Same pattern, no human anywhere in the loop. From consumer logins to giant backend systems, it is the same 2 ideas wearing different clothes. A few honest warnings before you ship this, because the details are where people actually get hurt. 1. Keep the expiry short. A token that lives for a year is a token that stays dangerous for a year if it ever leaks. Minutes to an hour is the sweet spot. 2. Store it carefully in the browser. A signed token in the wrong kind of storage can be stolen by a malicious script, so this is a decision to make on purpose, not by accident. 3. And this is the big one. These tokens are genuinely hard to cancel. Because a server can verify a token entirely on its own, it has no easy way to know that you clicked log out 30 seconds ago. Until it expires, a valid token stays valid. That is the price of being self-contained, and exactly why those short lifetimes matter so much. So let us tie this together in 3 lines. 1. Open authorization lets you grant an app limited access to your account without ever handing over your password. A valet key, not a house key. 2. The app gets back a short-lived token, and very often that token is a signed one: header, payload, and signature. 3. The signature makes it tamper-proof, but the payload is readable by anyone, so it proves trust without keeping a secret. Permission, then assign pass. That is the entire button. If the login flow finally clicked, do me one quick favor: subscribe, because the next one in the series builds directly on this. We are taking apart sessions and cookies, how a website remembers that you are logged in at all, and why that turns out to be a completely different problem from the one we just solved. See you in the next one.